the topic we are looking at is the relaxation technique, a very common method to solve our governing equations through computational methods, and also through a method called as iterative technique. Relaxation technique is a very common, well-known, accepted method, and you will find that in most of the softwares. Okay, so few important things. It starts from the fact that we are looking at finite difference method based technique. So the governing equations or the PD in front of us has to be discretized through a difference method. Further, the relaxation techniques are employed largely for elliptical partial differential equations. So we have three categories of equations. One is hyperbolic, one is parabolic, and this one is elliptic. So for hyperbolic and parabolic we have other techniques, but for elliptic partial differential equations we use iterative methods, and commonly known as relaxation technique. And this technique can either be explicit or implicit in nature. So to understand this, let us take an example of a partial differential equations for the variable scalar velocity potential, and is governed by Laplace equation. So when the flow is inviscid, incompressible, 2D and irrotational, then the governing equation reduced to a Laplace form. Right, so we have a double derivative of velocity potential in the x coordinate system, and we have double derivative of velocity potential in the y coordinates. So now if we look from the eye of solving a equation for a computational domain, so in case of elliptical partial differential equations we know the boundary conditions, and the aim is to solve the equation for the domain. So if we look at the image here, this image, we have, let us say we have a domain and we have created a grid, a uniform grid in x and y. So the boundary coordinate systems are 1, 2, 3 on this side, on this side, this side, and the extreme right side. So bottom, top, extreme left and extreme right, we have the boundary conditions. So here the value of phi is known, but all the nodes that are inside this boundary conditions, we don't know the value, final values of phi. So this is where the technique will come into play. And how do we arrive at this? Let us look below. So we apply a second order central second difference to get the finite difference form of the Laplace equation. Okay, so if we choose a coordinate system, if we choose the grid point, let us say this, so in the x coordinate system for a second order difference, it is written as the value of phi at the forward point minus 2 times the value at this point plus the value at the previous point upon delta x square. Similarly, in the y direction we look at these points where x is fixed and rather I is fixed, and we move in the j direction. So we obtain a difference equation like here. This is an explicit equation. Now for the sake of discussion we can say that the above equation has 5 unknowns, which is phi I plus 1 j, phi ij, phi I minus 1j, then phi ij plus 1, phi ij is already from the previous term, the preceding term, and then phi ij minus 1. So there are 5 unknowns and 1 equations. Now if we look closely at the internal grid points from 21 onwards, 21, 22, 23, and if you look at these, there are 15 grid points. And if we write the difference equation for all the 15 grid points, we are going to obtain 15 unknowns. So there is a chance, or there is a way which is called as direct method. So there are going to be 15 equations and 15 unknown, and we can use a direct method, where a method called a popular method, Cramer rules, to find the equation. But this is going to be really tough because the matrix size will increase as the number of grid point increases. So a much apt method for this type of problem is to go for an iterative methods. Okay. So first, from the difference equation, we segregate phi ij on the left side and all other unknowns on the right hand side. And when we say iterative methods, we are iterating at a n, let us say at nth iteration, and then at the next iteration, which is nth plus 1. So what we generally are trying to find out is the value of phi ij at n plus 1 iteration, assuming that the value of phi ij at nth iteration is known. And likewise, on the right hand side, all the values at the grid points for phi I, the 5 points are known at the nth iteration. So we're trying to link the nth plus 1 iteration to nth iteration. So what we are saying that we want to find the value in the next stage at phi I plus ij at nth plus 1, and it depends on the previous stage at the nth iteration. So this step signifies how we proceed in the iterations, and this method is called as Jacobi method, right? Commonly known as Jacobi methods. So in this way, at the nth plus 1, we try to find the value of that particular grid point based on what is happening, based on the values from the previous iteration. So one by one, we try to update everything at the nth plus 1. So we obtain all the values at nth plus 1. So this is called a Jacobi method. So if you look at this situation, what we are saying is, let us try to find the value at value of the variable at the grid point 21. So it depends upon 22, 20, 24 and 2, right? So in the x coordinate, it depends upon 22 and 2. So 2 is fixed, 20 is fixed, and 22 is not known to us, but we know the value of 22 in the previous iteration. So we've put this here, delta x we know, these are all constants. Similarly, 24 we know from the previous iteration, we put it here. 2 is fixed because of this boundary conditions, and we find the value of phi 21 at nth plus 1. And then we proceed to the node 22. Here we put the value 23, 21 in the x coordinates, 25 and 3 in the y systems, and we find the value of 22 at nth plus 1. So that way we are updating the value line by line, moving in the x direction from left to right, and then slowly moving up from left to right. Now what if, what if we, for finding value of 22, if you look at this, if we look at this equation, 23 we can understand is, this is coming, we can understand this is coming from nth iteration because we don't know, but this 522 we already calculated just before arriving here. So we already know the value at n plus 1. So when we do that, instead of using n, when we say n plus 1, so plugging in the latest values into the difference equation to arrive at new values, this approach is called as Guass Siedel method. Again, very commonly used in the softwares. You will come across this term quite often. So this procedure actually tries to speed up the whole process. And how long we are going to repeat this? We are going to repeat when the value at nth plus 1 minus the value at n is less than certain values. Okay. Now another concept that is commonly used in the softwares and you will come across quite often is something called as over-relaxation. So those who have tried Fluent or other softwares, you will find those values where the software asks you to how much values of relaxation you want to put, and there are some default values, you can play with it. But what is the significance is, so primarily what we are doing is we are trying to update the values at the nth plus 1 iteration from the values what are there in n. So there are going to be new values. So sometimes the solution is stuck, it is not converging and it is other oscillating. There what we do is that we try to update the value of the variable at nth plus 1, but we say that it does not completely take the values, it does not take the values which is coming from the difference equations. Rather we say that we say that there is the new values of the variable at nth plus 1 will depend upon n, no doubt about that, but now we add a factor w which is called as the relaxation factor, and this decide how significant the new values will impact the previous values. So the value of w can range between 1 to 2, which is called as over relaxation. So we are making a bigger jumps, and less than 1 we are making when we are under relaxation. So it is this. So what we have observed that sometime the convergence can increase to 30. So this is a brief introduction about the relaxation technique, successive over relaxations, under relaxations, Jacobi method and Gauss-Seidel. Thank you.